Welcome back. So in the second half of this class, we are going to just talk about three illustrative examples. They are all very friendly examples of counting from the basic principles that we learned about in the first half. Okay, so let's just start with the first example. How many odd numbers are there between 1,000 and 9999 have distinct digits? So let's just kind of pause for 10 seconds to everyone read to see if the question itself is clear.
What's distinct digit?
Meaning 1, 2, 3, 4 is an example of distinct digits. 1, 1, 2, 3 is not distinct because one appeared, meaning all the 4 digits have to be different. Is the question itself clear?
Yeah.
Okay. So let's call the number, because it has 4 digits, let's just kind of represent it as A, B, C, D. Meaning A is the 1,000 digit, B is the 100 digit, this is the 10th digit, and this is the unit digit. Okay. And I'm going to use our notation again. Using the kind of multiplication principle, you could think about we are basically choosing the digit one by one. Okay? So what I'm arguing is I'm going to pick the unit digit first, and then pick the 1,000 digit, and then pick the 100, and then pick the 10th digit. So I'm going to say that this is the set of D, A, B, C. So for the unit digit D, how many choices do we have?
5.
Which 5?
1, 3, 5, 7, and 9, because an odd number adds to this.
Okay, cool. So D can choose from 1, 3, 5, 7, and 9. What about the second choice, A, which is the 1,000 digits? How many choices do we have?
9.
Which 9?
1, 2, 3, 4, 5, 6, 7, 8, and 9.
1, 2, 3, 9. It cannot be 0 because it's the leading digit. But there's one more condition. Because after we pick D, if we pick D as 1, can A be 1? So the way that we would describe it then is D can choose from these 5 choices. A can choose from 1, 2, 3, 4, 5, 7, 9, and then minus D. So I hope it becomes a little clear about why in the first class. we talk about this kind of set notation, it just makes it a little bit easier for us to describe counting. Does everyone agree? So A can choose now 8 choices. We don't know what D is, but it's going to be 1 to 9, subtract D. What about C? How many choices do we have? I mean B. We should do B first. Anyone?
10, because it can be 0 to 9, but minus A and B.
Mm-hmm. And then minus D and A. Okay. Last one, the unit digit. How many choices are there? So it's 1 to 9 and minus, it cannot be D, it cannot be B, it cannot be A because those are already chosen. And we know those three are different. Okay. So then this is the application of the multiplication principle. Where you count those sets separately and then multiply them. So D, you have 5, A, we have 8, and then B, we have 8 again, 0 to 9, but then minus D and A, and then C is 10 minus 3 numbers, so it's 7. Can I get a show of sign? Okay. Now, this is the application of the multiplication principle. But the reason we pick this principle, we pick this example question, is it illustrate what I think is a pretty important point. The choice of this order is very important. Let me illustrate some other choices of order and why those other orders would not work. Let's say we were to say we would pick the thousands first. Again, n is A, B, C, D. Meaning if we choose A first, and then choose 100, and then pick 10, and then pick unit. Then we can basically say A has 9 choices, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 9. And then for the 100, how many do we have? 8. Okay. 9. Yes. Sorry. Great. 9. And then C we have 8. And then what about D? We have a big problem because the answer of D is it depends. Did we already choose some of the odd numbers? Let's say if these 3 we pick 2, 4, 6, then you still have 5 choices on the unit digit. But if you have picked 1, 2, 4, then you only have 4 choices left. 3, 5, 7, 9. Let's try another order. Let's say we say, okay, let's do the units first. And then 100. And then 10. And then 1,000. How many choices do we have for unit? 5. What about 100?
9.
9. What about 10?
8.
8. What about 1,000?
7? No. 6?
Unfortunately, this is another case of now it depends. Because if we have chosen 0 somewhere here, if we have chosen 0 here, then it is 8. But if we didn't choose 0, haven't chosen 0 yet, then we will still have 8. If we have chosen 0, then it is 8. Are you with me so far? So, the way we've done it is we pick unit, and then 1,000, and then 100, and then 10. And that sequence or that order of choices is very important to how to be able to solve this question together. Because we don't know what the unit digit is, 1, 3, 5, 7, or 9. But then no matter which one we have chosen, we know that we can still choose 8 numbers from the 1,000 digits and so forth. Can I get a show of sign for this part of the discussion? How does everyone find this part of the discussion? Okay. Okay, so let's go to the second friendly example that we have. How many integers between 0 and 10,000 have only one digit equal to 5? So I'll pause for a few seconds, make sure everyone read the question, and the question makes sense to you. Okay. So we're going to pursue a solution. We try to split the count into a few subcategories. Does anyone have a suggestion on how to split it?
You split it into each 1,000 and then divide it and then multiply by 10.
Can you say it again? Multiply, or split it into each 1,000 and then multiply by 10.
Oh wait, actually no.
Yeah, that does not work because clearly the
Hundreds.
5,000 something is, there's only one, which is 5000. So I'm going to do this counting. So we're going to split it into 5 groups. Those that have only single digit, 2 digits, 3 digits, 4 digits, and 5 digits. For example, S1 is 0 to 9. And how many numbers between 0 and 9 has only one digit of 5?
1.
1. And there's only one number with 5 digits, which is 10,000, and it's not a 5, so it is equal to 0. So now let's look at S2. So first of all, 2 digit is between 10, 11, 12, all the way to 99, right? So the way that we are going to do it is, because it has to have at least one digit of 5, right? So there are only two possibilities. It's either 5 something or something 5. Do you agree? By the way, so here we are again applying the addition principle. We are splitting S2 further into two non-overlapping sets. How many choices are there for 5 something?
Ten?
So 5, 0, 50, 50, 51, 52, 54, 55, 56, 57, 58, 59. But 55 doesn't count,
Oh,
right?
yeah. Slow down.
So it's 9. So what about this one?
8.
Which 8?
15, 25, 35, 45, 65, 75, 85.
Okay. So now ask 3, how many groups do we split it into? So again, using the addition principle, we want to be able to split it into a few non-overlapping groups. So I'm going to propose that we split it into 5 question mark, question mark 5, and then question mark 5. Olivia, how many choices, how many numbers are there in this group? 5 something something?
100.
Which 100?
500 to 500 to 599.
Does 505 count? No. So the first digit of 5, the second digit can be 0, 1, 2, 3, 4, 6, 7, 8, 9. So how many choices with that?
10.
Not 5. Because the second digit cannot be 5.
9.
9. What about the third digit?
8.
8. So now this one. Wait, this is also 9, now that I think about it.
Why?
Because they give me the same number. But I thought you gave me the same number. But not
Okay, what about this one?
It's the same.
72?
Mhm.
9 times 8?
Why is that?
Because the first number, the first digit can't be 0.
Mm-hmm.
Oh, shoot.
So this is 8, 9. So do you get it? The first digit cannot be 0 because we are counting a 3-digit number. So similarly. So we're almost there. So how many choices are there on this one? Yes. That would be 9 times 9 times 9. What about this one?
Hmm.
9 times 9 times 8.
Mm-hmm. Yep. Similarly for the other two. Okay, then the last step is to add these three numbers. Can I get a show of sign before we get to the last example? Cool. So let's get to the last example of today. So I'll give everyone a couple of seconds to kind of read the question. So n is the number known as 2022 factorial, which is 1 times 2 times 3 all the way times to 2022. And the question is, how many zeros does the number n have at the end? Is the question clear? It's a difficult question, but is the question itself clear? So principle number one, when the question is really hard, what do we do?
Use smaller numbers.
Just use a small number. So give me a small number.
3.
3. 3 factorial would be 6, so it would be 0. But let's say 5 factorial. How many zeros do we have in the end?
1.
Why?
120 has 1 0 at the end.
Okay. Number of, let's just call this ending zeros. One. If we do 10, we are not going to multiply it. But how many ending zero do you think it has?
2.
Why?
Oh wait, actually never mind. It's not 2.
I think
Wait.
it is 2. Because 10 times 1 and 1 is
Yeah, it is true. So what about, let's say 15? First of all, 15 factorial is 10 factorial and then times 11, 12, 13, 14, and 15.
3.
Mm-hmm. Where did we get the extra zero?
Because
15 times 12 is 180 and 180 has a 0.
Okay. Now, it seems like we have some intuition after we've done a few. We are not really multiplying all the numbers, right? you chose to multiply 12 and 15, and you basically ignore the number 11, 13, and 14. You basically say they are not, like those three numbers do not give us any zero in the end.
Yeah.
I think intuitively this is kind of what you made the decision. Okay. So let me explain how this is counted. Every integer n can be written in a kind of prime factorization, right? So let's say 2 to the power a, 3 to the power b, 5 to the power c, and so forth. Now, if we count number of 0 that n have in the end, can I convince you that we actually do not care about this part? They're not going to add 0 to us in the end. So what
is it? What happened to 4? Why did it just do 3 and 5?
So for the number, let's say 4 factorial, it would be written as 4 factorial, right? So it will not have 0 in the end.
Yeah.
5 factorial, on the other hand, is 2 to the power 3 times 3 times 5. And you basically notice that you get 110 in the end because you get a 5, you get a 2 from here. And then for the 10 factorial, there's some power to the 3 that you also don't care. What is the power of the number 5 for 1 to 10?
2.
Which numbers did you get the 2 from?
The 10 and the 5.
The 10 and the 5. How many power are there in 2?
8.
I didn't know whether it was 8 or not, I didn't count. But one thing you develop is usually 5 is the limiting factor. Are you with me so far? So basically for you to calculate how many zeros are there, what you want to count is what's the power of 5, and that is basically the number ending 0 for you in the factorial question. Maybe let me give a different example. Let's say if you have a number, it is 2 to the power 10 times 5 to the power 3 times 7 to the power 13, 13 to the power 2. Then I ask you how many ending zeros are there in this example. How many ending zeros are there?
3.
Yep. Because you know once you multiply this, you basically get 10 to the power 3. And then other numbers you multiply to get something on the left hand side. So all you care about is basically how many 5s are there.
So does that mean you divide any number by 5 to get the number of zeros at the end?
Very close. We'll get to that in a minute. But counting 5, number 5, will be equal to the number ending 0. Can I get a show of sign? And then let's begin counting the number 5.
Number of 5s, but wouldn't there be like 25, which has multiple 5s? And 125? So,
Yeah,
so how much?
that's basically the answer. Once you count number that can contribute 2 5s, and 3 5s and 4 5s. That's the answer. But before we get to that, let's say how many 5s, how many multiple of 5s are there? I think Naomi just said that basically it is this. So this is 404.4. And there's a symbol that basically means rounded to the integer. So that's 404. And Rafi made a point about 5, 10, 15, 20, all of this contribute to 1, 5 in the factor. But how many 5 does the number 25 contribute to the prime factorization? Is not 1. How many does it contribute to? 2. Because 25 is 5 to the power 2. Then that means when we look at this, every 5 number added 1 5 to the prime factorization. But then once every 25 numbers, it adds 2. Again, the first 5 is already counted here, so we only count the addition of the second 5 that the 25 contribute to. Is that it? Is 484 the answer? What else?
So 7 multiples of 125, 6, 25.
So this is basically then the answer.